Okay. Wait, let me download this. Okay. Okay. Sorry for the late start. So, any question from last time? So last time we finished the Shor's factoring algorithm, and once again, let me try to find this. Okay. Once again, the core part of Shor's factoring algorithm is this order finding algorithm, where hello, wait, okay, maybe if I do this, okay, where the core the core part is this order finding algorithm, and what you want to do is you have some number n, and so n is not necessarily prime, and but anyway we have x that's co-prime to n, and we find the number r, which is called the order of x with respect to n. That is smallest integer, such that if you keep multiplying x with itself, so you hit at x to the rth power, and you find out that x to the r equal to 1 mod n. Okay. So this is the order. This is number theoretical thing, and we have shown that if for any pair of x and n, you can find this. Why is this so weird? Hello? There's some weird. Wait, maybe if I. Okay, hello? Okay. If I get further away, like this, wait. If I turn down the volume. Hello? Okay. Sounds a bit better. Yeah. So this R is the order, and for every pair of x and n, you can find this R very efficiently, then you can solve factoring very efficiently. And the exact number theoretical thing is quite complicated. But basically you want to find even R, and then you so if you are lucky your R is even, then you calculate x to the r over 2, and if you are lucky again, then x to the r over 2 minus 1 will have a common factor with n. That's how you factor. And now the quantum part of this order finding, you have different ways to look at it. So the first way to look at it is you do a phase estimation on this unitary gate, which is multiplication by x. So this thing just turn a computational state y to another computational state xy, but everything is modern. So this part is oh, sorry. So this part is some bigger dimensional thing because everything is modern. Anyway, you have this unitary x, and then you think about you should call you what's it called? Anyway, so you think about a subspace or invariant subspace that is you multiply x on 1, so you will get things like 1 x squared all the way to x to the r, which is also equal to 1. So this is some r-dimensional subspace that's invariant under this ux, and there is r-dimensional, so there are eigenvectors, and those eigenvectors look like this: is x plus x squared plus all the way to x to the r, or if you multiply some phase omega to some power. And so in short notation, look at this. So you sum over all the x to some power, where this some power from 0 to r, and then you have this phase e to the 2 pi I over r. So we call this omega. E to the 2 pi I over r with a minus sign. So we call this as omega. This is the rth root of 1. Then you times it to the s times k power, where k is this k and s is a subscript, it will determine the phase of this, determine different eigenvalues for different eigenvectors. And anyway, so those are eigenvectors. They are equal superposition of x to the k, and multiplying different phase vector. And their eigenvalues will be this omega to the s. Oh, sorry, minus omega to the minus s. But anyway, it's exponential 2 pi I s over r. So you see this has some information about r. And so the idea of short period finding algorithm is that you take this unitary, then you do a phase estimation, then you will learn s over r. And another problem is it's very hard to construct a specific UIs, but you find that 1 is actually a uniform superposition of all UIs. So if you use 1 on the eigenvector register of your phase estimation, then you will get a random s over r. So you get a whole bunch of random s over r, you will learn r eventually. And so that's the first way to see short period defining algorithm, where you do phase estimation on this ux and eigenvector 1. And you can also write down the algorithm and see it in another way. So if you write down the phase estimation, exactly look at this. You create an equal superposition of some number, and you have 1 on this phase. Then you do control, this TB control of multiplication x on this one. Then you can think about you measure here, then do a QFT minus 1. And so you think about what happened after you do the multiple control multiplication is that, well, first register, obviously you have a whole bunch of integer. That's why we do a whole bunch of HEDMA here. So you have equal superposition of integer from some number 0 to n minus 1. Then you apply multiplication to k's power. So multiplication by x to k's power, so obviously you have x to the k on the second register now. Then you measure the second register in computational basis. And now is where the number 3 come in. Now remember, once again, this s to the k only have different values. So it's some cyclic thing from 1, well, we start from x, but we come from 1. So 1 x squared all the way to x to the r minus 1. Then x to the r is also equal to 1. But then, so there are only those different values. And so when you measure this register, you will get one of those values. And then the quantum part happens, you get one of this value, then you will also collapse the first register to the corresponding values. And those k that give you, so let's say you get random k is one of those possibility. And then the first register will also collapse back to the corresponding k's. So it's k and then k plus r and k plus 2r, etc. And there are some number of these registers. And for simplicity, we assume r is actually a factor of n. Then, yeah. And then we can look at this like a post-trend. So we can get some intuition by thinking about this as a post-trend in terms of signals. So it's equally spaced all things. And then we know we do a inverse Fourier transform or Fourier transform. Then we'll get another post-trend, but the starting point is actually become 0. And the spacing, so if the spacing here is r, then after you do Fourier transform, the spacing here will be like 1 over r. Might have some constant depending on how you normalize things. But anyway, then you get spacing 1 over r here, and you do a measurement, then you also see random s over r. Okay, and there are some scaling, bigger and doesn't really matter. Anyway, so you see that with this HR analysis of you do measurement here, you also see you will get a randomness over R. Then you get a whole bunch of these, you can learn R. Okay. And so that shows period finding algorithm. And obviously we make this assumption that's not true, which is R divides N. But if R doesn't divide N, then you get a whole bunch of error everywhere, and you need to analyze your error carefully. And that's similar to the analysis in phase estimation, so we skip that. Okay. So that's a review about short factoring algorithm. And I think that's the only quantum thing we are going to talk about today. So now we'll talk about classical thing, more classical thing, classical number theory. It's about things related to this thing. Or, well, I guess more practically, we are going to talk about why short factoring algorithm is useful. That's the RSA crypto system. But before that, we are going to talk about some number theory and algebra for number theory. Okay, so this is going to be a totally classical, or not even classical, it's a mathematical course today. And it's not so much content, so we'll probably finish early. But anyway, any question on this short algorithm? Otherwise, let's go to our number theory. Okay, I guess I can close this one. Okay, so RSA group theory. So let's gonna get a quick review first. So how many of you have heard about a group? I guess raise your hand. Oh, a lot. Okay. So this will be easy for you guys. Okay, but anyway, for lots of we'll still go through everything. So a group is well, in a very abstract form, it's a set with an operation. Okay. So here we are taking things easy, so we have a finite group. So we have a set with a finite number of elements. And there is also a multiplication operation associated with those elements. And this operation needs to satisfy a whole bunch of properties, as we will introduce later. But for a quick, easy way to visualize a group, you can just think about those elements as some n by n matrices. Okay. This is, I think, the most natural way to think about groups. And mathematicians also, well, mathematicians like to abstract things, but they also secretly like to think about groups as n by n matrices, and this is really cool. And they develop a whole theory around this. It's called representation theory. So representation theory is a lot about how to write your group in terms of matrices. That's some digression. Okay, so let's write down this representation. Okay. So representation theory is mostly about how to write your arbitrary group into matrices. And well, there are arbitrary groups that you cannot write in matrices, but that's a really far away digression. Anyway, so what does the group need to satisfy? So I guess the thing we didn't say is, oh, well, it's here. So first thing, you have multiplication, and multiplication needs to satisfy closure. So multiplication is an operation that takes two elements from a group, and you can multiply them together, and you will map to something that's also in the group. That's called closure. When you do multiplication, you also go back to this group. And I guess this also makes more sense if you think about these n by n matrices. So you have you select a whole bunch of matrices as your group, and then you do a matrix multiplication, and you also need whatever result you have, you should also be in the set you select. Okay? So you need to have closure. And then the multiplication, you do need to satisfy associativity. Well, that's just this. And usually you have this. Oh, it's really annoying. Can we close the door? Will it be better? Can someone close the door to make the noise a little better? Okay. Yeah, so associativity, so you have A times B times C. Then if you do the multiplication on BC first, then that'll give you, let's say if you are matrices, that'll give you another matrix. Then you multiply this matrix with A. Or you do in reverse order, you do A times B first, then just give you another matrix and you do multiplication with C. So this ordering doesn't change the multiplication result. Then that's associative. Okay. So this is directly satisfied by matrix multiplication. And the identity. So the set of things, so this set of things inside your group, these A, B, C, D, E things. So there must have an element that is identity. And it's usually denoted as E. But in terms of matrices, we have say the identity. That's just the identity matrix ID, right? So if n by n matrix is like 1, 1, 1, 1, 1, and 0 other way. And the identity means everything multiplying it must get back to the same thing. So it's like 1 in multiplication. And so now things are a little bit tricky because we are thinking about matrices, right? Well, not really matrices, because this is really abstract. So the multiplication is actually not associative. So AB not really necessary, AB not necessarily equal to BA. So there is a left multiplication and a right multiplication. But anyway, identity need to satisfy that either you multiply on the left or multiply by the right, it should give you back the same element. And yeah, so that's identity. Whatever thing multiplying with the identity should go back to the same thing. So every element A in G, you multiply it with identity to the left, you go back to A. You multiply identity to the right, you go back to A. And then you need inverse. So inverse means that well, this is also like anyway. So inverse is the inverse identity for the group says that every element in the group there must have an inverse element, and inverse element means that if you multiply your element, so there is actually two different notations. So there is a left inverse and the right inverse. And you can prove that actually left inverse will equal to right inverse, and we'll skip that here. But anyway, so inverse element will satisfy the property such that if you multiply A with A minus 1, you will equal to identity, or you multiply A with A, you will multiply A minus 1 with A, you will also equal to identity. So this should be minus 1, so I should, let's make this more clear. So A minus 1, and this is A minus 1, okay? And you can also see this in group, right? Although groups multiplication doesn't necessarily commute, but if you have inverse matrix, so you have some A and A minus 1 equal to the identity matrix, then you probably learn in linear algebra such that A inverse is also equal to A inverse times A also equal to identity. Okay, and so that's actually quite general for a group. Whenever you have left inverse, that will also equal to right inverse. But anyway, we are not going to prove that. Here we write it once again, such that for general groups, the multiplication is not necessarily commutative. So I should say, okay, there are too many names. Right. So this is the difference between, say, like integer multiplication or group multiplication. Integer multiplication or matrix multiplication. For integers, a times b will equal to b times a. But if those are two matrices, then a times b not equal to b times a. So for the general definition of a group, this multiplication is not necessarily commutative. So for those that are non-commutative, it's called non-abelian group. And otherwise, if the multiplication are commutative, then it's called an abelian group. And actually, we'll focus on this today. We only need a abelian group for number theory. Anyway, it's nice to know there are differences. Okay, so up to here are the definition of a group. Any question? Okay. So I guess a very quick example of a group is the polygroup. So we learn we have those three polymetrics and identity, right? So we have sigma x, sigma y, and sigma z. And let's assume we ignore the face. Okay. So let's assume matrices times face is the same matrix. And so if you have a sigma x, sigma y, sigma z, and identity matrix, that's called a polygroup. So modular some face like I or plus minus. Okay. Why? Because we have closure, right? Because we have say like sigma x times sigma x that will equal the identity, so that's in the group. And like sigma x times sigma y, if you still remember, that will be sigma z times on face. And all the cyclic things. So so it has closure, and obviously the multiplication is matrix multiplication. So that's associative. I guess if we say this is a abelian group because sigma x, sigma y equals sigma y to sigma x. Anyway, and identity, obviously we have identity matrix here. So there is identity. And so for inverse, so every element is its own inverse, because we know sigma x squared equal to identity, sigma y squared equal to identity, and sigma z squared equal to identity. Yeah. So those are group, and if you want to be non-associative, then you need to distinguish like sigma x, and so every one of those should split into four. So you have sigma x, then I sigma x, and minus sigma x, and minus I sigma x. Those are different elements. And when you do multiplication, you also need to check the face, etc. Okay. So that's an example. Anyway. And then we need to have more concept here. So very important thing about group is the number of elements inside. It's very important, so you have a special name. It's called the order of the group. Okay. So order of the group is the number of elements here. So for example, here the order is 4. Well, if you are not distinguishing the face, 1, 2, 3, 4. And it's also denoted with this absolute value G. So this is basically a standard set notation, right? You take absolute value and you think of G as a set. And absolute value of the set is the number of elements inside. Okay? So this should be pretty intuitive. So that's the order of a group. And then now we go into more structural things. So sometimes there can be things called a subgroup. Okay? So what's a subgroup? It's a subset of a G, and it is also a group. Okay. that we didn't say here, but it's also a group under set multiplication. Okay. Okay. And so it must be a group. So under set multiplication, and we didn't say, but identity is going to be unique in a group. So, and anyway, in terms of subgroup, this means the subgroup is also a group, so the identity must be inside your subgroup. And actually, the hardest thing to satisfy a subgroup is closure. So, in order for some subset to be a subgroup, so you think about a whole bunch of elements inside, and you can multiply in like each pair of them, and they need to be stay inside this subset because it's also a group, so it needs to satisfy closure, and so you need to select this set carefully such that however you multiplying them, they will be also inside this subset. And we'll see later that if you have closure and you have identity, then you also satisfy inverse. Yeah. So anyway, so that's a subgroup. Is something that's a subset of your group, so some fraction of your group that also satisfy those for properties under the same multiplication rule. Okay. And then there is this group theory result that are not too hard to prove, but we will not go into a detail, saying that if you have a subgroup of a group, so if H is your subgroup, then the order of H divides the order of G. Okay? So order of H is an integer, order of G is another integer. And this is actually very useful. It lets you classify your groups a lot. Let's say, for example, although we will not use too much. For example, if let's say your order of your G is a prime number, right? Then you know there are basically no subgroup because only C divides your prime number is either, so if the order of G equals to some prime number P, then anything divided your prime number P is only 1 over P. And well, if a subgroup has order P, then basically it has anything, so it's something trivial, right? Obviously, your G itself is your subgroup. Okay. But so this order P subgroup is trivial because it contains everything. And what about order 1 subgroup? Well, order 1 subgroup is only identity. Okay. Because we have said subgroup must contain identity. And we didn't prove, but the identity is also unique. I should put it right here. Okay. So identity is also unique. So so yeah. So the thing that contains identity, there is only one of them, and it is always going to be a subgroup of any group, because identity is the inverse of itself, and there is obvious closure. If you multiply identity with identity, it becomes identity. Yeah? So identity is a trivial subgroup, and anyway. So we know that if G has a prime order, then it has no non-trivial subgroup. The only subgroup is itself or the identity. So that's quite interesting. And if G is not prime, then there are more interesting things you can say. Okay. So that's group theory. And once again, we say that. Now this is an extra label you can put on group. It's a abelian group, and that's when your multiplication is commutative. A times B equals to B times A for AB inside your group. Okay? And as we say, we'll focus on abelian group today. And actually, a abelian group can be totally characterized by just this. We'll see a bit today. Okay. Anyway, so let's go to a very good example of a abelian group. Okay. So that's the multiplication group mod 7. So this is a thing we have been keep touching, right? A bit like order finding thing. So anyway, so we're gonna think about everything that's co-prime to 7. So that's 1, 2, 3, 4, 5, 6, right? And and so we have those elements, and now the multiplication is just integer multiplication. Okay, integer multiplication mod 7. So integer mod 7. Okay. So this is a group. So we'll check all its property. And so is this closure? Well, so yes, because if we have two elements A and B, let's say it's A and B, and well, A and B is inside this set. That means A is not a multiple of 7 and B is not a multiple of 7. Then if we take integer multiplication of A and B, then it's also not a multiple of 7. This is by, I think this is called fundamental theorem of arithmetic. But anyway, by elementary school math, we know that if A doesn't contain a factor of 7 and B doesn't contain a factor of 7, then A times B doesn't contain a factor of 7, then A mod B must, so we know A times B mod 7 must be one of those 6 things. Okay? We may not know what it is, but it's not 0. Okay? So we have closure. And associative, that's just from integer multiplication. We know A times B equal to B times A. Then A times B mod 7 equal to B times A mod 7. And what about, do we have identity? Yes, 1 is identity. You multiply everything with 1, you get to the same thing. Okay. Now, inverse is a bit harder to prove. Okay. So this is the thing we said a little about in the subgroup. When we talk about subgroup, we say that we have closure and identity we must have inverse. Now we actually give a proof. Okay. So the proof is like this. So you think about, well, actually you can do more, but anyway. So you think about you have some element x and you want to find its inverse, right? So the question is, what is x minus 1? So you have some x and you want to find x minus 1. X minus 1 equals to what? And then you just start listing things. So you can have x, and you have x squared and x cubed, all the way to x7. Okay, so everything here is like mod 7. Because we think about how those things are moving around inside your group. Okay? And okay, so you have x1, x2, x3, all the way to x7. And but now you can apply pigeonhole principle, right? Pigeonhole. Because now you have 7 elements here, but you see only have 6 elements here. Okay? So those 7 elements must have some collision with each other. So 2 of them must be the same, right? We don't really know which 2, but there must be 2, because you cannot squeeze 7 different things into 6 holes without some collision. Okay. So there must be some A and B, and let's assume A less than B, such that x to A equal to x to B mod 7. Okay. We are just try to squeeze everything inside. and then we can do more arithmetic. Okay. Then if we divide by a to a on both sides, then you have 1 is equal to x to the b minus a minus 7. And this is where we said all this nicely. So b times b minus a is a positive number. Okay? And b times a is also not 0 because a and b are different. Okay? And so this actually proves something that we claimed is true previously. So, right. So this is where we have this kind of thing. So we should prove that this order always exists. So, excuse me. Yeah. So this b minus a is also equal to r. But anyway, we have this x to the b times b minus a minus 7 equal to 1. Then we can also, so we should say here, right? So this is b minus a is actually equal to order r with respect to n, with respect to 7. But it also bigger than 1 and less than 7, I think. I guess it's not necessarily r because it can be like 2r. It's about r, and it's bigger than 1 and less than 7 or 6, whatever, doesn't matter. Let's just say it's bigger than 1. Okay, so b minus a is bigger than 1, so we can take another minus 1 here. So x to the b minus a minus 1 times x equal to 1. And this is still positive because, well, b is bigger than a, so b minus a minus 1 is at least 0. And okay, so this is, so b minus a minus 1 is at least 0. And anyway, we know x to the this b minus a minus 1 is the inverse of x, right? Because when you multiply x with it, it becomes identity. Okay. So, any question about this proof? This is how you prove this. I guess this proof this I. It prove that such that satisfying this relation exists. Then, well, r exists, then there must also be a smallest r. So, this proves that this order exists. Okay. So, yes, this is also why this algorithm is called order finding, although I've been also calling it period finding. So, this is sort of order finding because that's the order of the subgroup generated by x, right? So this will be a subgroup of this multiplication group. Just all the things that are some power of x, and we're finding the order of subgroup, so that's called order finding. But we are also thinking as this is a period of some periodic function, so it's also called period finding. Anyway, that's why this is a group, because it satisfies all those 4 relationships. Then we also have, so the thing we also talk about, so what's the order of this group? Well, obviously there are 6 elements, so the order is 6, and now we know 6 is 2 times 3, and actually they are subgroup. So if you have non-trivial subgroup, they must have order 2 or 3. And so here we give example, and so we immediately get 2 examples. of subgroup that have order 2 and 3. So a subgroup of order 2 is this set 1 and 6. And it's easier to see if you think about 6 as minus 1. Okay? 6 equal to minus 1 minus 7. And minus 1 squared become 1. Okay? So 1 obviously times everything is itself. Minus 1 times minus 1 become 1. Okay? So this is a subgroup because you multiply everything, then you go back to this. And another subgroup, and these are 2 elements of order 2. And another subgroup is this group of 1, 2, 4. So you can think about this subgroup as generated by this x equal to 2. Right? So 2 times 2 become 4. Then 4 times 2 become 8 equal to 1. Okay. So this is order 3. And so you see everything times 2 goes back, and also so for the multiplication you also have, I guess you can have 4 times 4, then 4 times 4 equals 16, then equal to 2. So everything go back to this subgroup. And just as we said, in general, you can just generate a subgroup by take out some element, let's call it a generator. Then you just keep multiplying it by itself. So you have x times x become x squared, and times x become x cubed. And keep doing this. Then you find out, well, there are only finite number of elements. So eventually you will come back to itself. And when you come back itself, you will get some x to the r that's equal to identity. And x to the r equals identity, then x to the r, then you have x to the r plus 1 equal to x, then you hit yourself. Okay? So this is a way to generate subgroup. Okay. Any question? No? Okay. Then, so this is multiplication. So you can see that if you change 7 to other prime number, then you will have very similar groups. You can have 7 to 13, 17, then your group will have similar structure. So those are prime groups, but if you can have things that have more structure, so like if you have mod set, so you have mod any prime, you have multiplication group mod any prime, then you will see you will have like 1, 2, all the way to p minus 1. So you have p minus 1 elements. Okay. So the prime group all are really similar. You can see that. Obviously, you can go through the same proof to see that they are a group, and obviously the order will be p minus 1, and you can find subgroups in this way. Yeah. So those are multiplication group mod p. Now we go into some the group that are actually using RSA. Now it's a multiplication group of some number n that has 2 prime factors, so n equal to pq. Okay. And so yeah, as we said, we assume n is multiplication of 2 prime number p and q. Okay. And now we want to think about multiplication of this group of this. So we want to think about elements A. So we have some elements, and then we want to think about multiplication of A times B mod n. Okay. So if your multiplication operation is like this, and And then the first thing we define is the order of this group. So the order of this group is we give it then as this psi n. Okay. So psi n is the order of group, and the order is the number of x, such that well everything is modern. So we have x from 1 to n minus 1, and now there is something different, something a bit different, right? So when we talk about prime group, we want thing because it's prime, so we just have things that are from 1 to p minus 1. But here we are at least to be stricter. So when we generalize that to n that's not a prime number, we want GCD of xn equal to 1. So basically x and n are co-prime to each other. And why we want this is because we want every element has inverse. Okay, so you cannot have so even if let's say so basically you don't want the PQ inside your group, right? If you have a P and a Q inside your group, then P times Q equal to n, and then Q equal to n equal to 0, but 0 don't really have an inverse in your multiplication, right? So n should not be in your group, then P and Q should not be in your group, and any multiple of P and Q should not be in your group. Okay. So that's the idea. So anyway, so the elements in your group are things that are co-prime to n. Okay. And now the question is how many elements are actually here. So what's the order of this thing? And we claim the answer first. The answer is that the number is p minus 1 times q minus 1. And you can see this from easy, well, this is not quite a proof first, although we'll prove this is correct. But you can get an intuition from just probability. Right? Because, so if you think about things from, let's say, oh, what is it? Okay. Let's have a break and let's talk about this next class. Okay. Okay. Let's have a 10 minutes break.
这里为什么它0乘上1的时候，它最后会多出这一项跑出来？
可能从下面那个看比较快，这个怎么算？最后面那个没有0就只是用来写数字嘛，0是这个东西啊。所以0跟1，然后你做完 face estimation， 然后最后它会把 face 写在0这里嘛，就是这样子。
好。
两边都除啊，不行吧？应该可以吧？都除 x 对。啊？
还没有inverse要怎么
就先不骂的除下去嘛。
还是要先用整数？
对。第一个，这个总之是 exist 嘛？我想想看，你是说这样？
就这边要统称 x 的部分，就是除 a 还是这样？
我想想看。如果我想想看啊，我不在这个里面的话， 证明 x 除了7是，你要证明 x7是1，是0。这样，有没有比较简单的？这样的确不太那个，对不对？有没有比较简单的证法？我想看看。我觉得这个有很残暴的刑法。这样子会被过啊？我想想看。好像不会过。所以我们写出来的话是。需要有一个词。我可以写成 x 除了 b 减 a 乘以 xa 等于 xa。但是我这样是没有 x 除了 b 减 a 等于1，对不对？所以我需要有uniqueness。好，怎么证呢？我忘记了，上次应该就有可以认出uniqueness。应该有类似uniqueness的东西是怎么证的？暴力做。对。先偷懒这个东西叫做个语法。没有，所以我要用uniqueness overidentity。可是我还不知道它是 glue 对不对？
陷入这个循环。
陷入循环，好。OK， 所以我把这 uniqueness 证完，但总之依法，我没有注意看吧。依法看是 x 除了 a 减去等于 x 除了 a 加上 c 乘以 c。OK， 这样子应该就可以看出来。然后，所以这里没有 factor of 7，所以这里一定要 factor of 7。对吧？所以7会divide 1减1，1等于1 7。要拉回 fundamental theorem。
所以是从这里，
把它拆成这样。
然后把 b 乘以 b 减 a， 然后在这里这个东西就是
这个东西减1之后要是7的倍数。
先回到整数，
对，先回到整数的。 嘛，这样。
那个什么整数的，那个
没有，这个只是我假设，只是要让它写起来方便而已。如果不整数的话，你就会多一堆 error，然后就很恶心。这个只是方便写而已。如果没有的话，你就要跑 face estimation 的那个。face estimation 我们不是在那里说 face estimation 如果它不是在正中间的话，它会什么？如果你的 phi 在这里，然后它就有什么归 distribution 的事情嘛？这就是 R 不出圆的时候。我们 R 出圆的时候，就是那 face estimation 刚好在一个点，然后什么都很漂亮的时候。对应回去后。对。分一些文献看一下，就是 R 如果不出圆的话，那就等于是你 face estimation 的时候，那个不是刚好的 B stream 嘛？我们 face estimation 的时候不是在说什么 phi 等于0点 B1 B2 到 Bn 嘛？对，所以如果 R 不出圆的话，就会对应到这个是那个后面还有很多东西的情况下，然后你就会有那个很奇怪的东西，然后你就要跑我们 face estimation 的放那个那些事情。
不整数就是会有后面。
对，就是会有后面这些东西。
昨天有再重新看那个 face estimation 看总分计。对，还没招到他精神。
有点是暴力也算了。精髓是
这边就 phi 嘛，然后他找一个 b 小于 phi 最接近他的一个 b 这样。
我们不是去最接近的是，我们是直接去 floor 的，我们是直接去 floor 的 ，B 我们是直接去 floor 的。对 ，B 直接去 floor。
然后 phi 有小数。
对啊，我们就直接把角线后面去掉，对。然后我们说我们有一个我们允许的误差叫1嘛。然后我们就去帮的 tail 做 tail 很小 ，tail decay，tail 是用这个，然后这个长度又叫1又叫 L 的，我们就这个长度叫 L。
出来的结果大于1的几率。
对啊。
然后去帮的这个东西会小一点，
对，我们是说就是直接微积分看还有的嘛，我们是说这个东西就大概是1/1 square 这样。然后你知道微积分。你有个 tail 是1/1 square 的话，那其实你积分到无限大的话，它也是会那个会 converge 嘛？就你这个积分1/1 square，然后第1的话，这个会大约等于1/1嘛？对，有帮助。
但是这个只是 n 跟 b 的距离，那还有 b 跟 phi 的距离。
就B跟 phi 距离不重要吧？那也就不会超过1这样子。B跟 phi 距离就不会超过1嘛。
好，
对。对。Okay. Hello. So any question? Yeah. Okay. So I need to correct this a little bit. So as point out over the break, we are doing this slightly two-faced here. Okay. So from here to here is not too obvious because we don't have x to the minus a already. So let's do this carefully. So we have x to the a is equal to x to the b minus 7. then we can separate this into x to the b minus a times x to the a, and this is equal to x to the a minus 7. And so how do we say this is identity? So it is equal to 1 minus 7. Then we need to go back to integer. So x to the b minus a times x to the a equal to x to the a plus 7 times some number c. Okay. Then we move things around. We have no, this. Then we move things around. We have x to the b minus a and minus 1 times x to the a equal to 7 times some integer. Then we look both sides, so we have a 7 here. And we know x is coprime to 7, so x to the a is also coprime to 7. So this has some factor of 7, then this must have some factor of 7. Okay? And that tells you, so this has a factor of 7. In full notation, we write 7 divides x to the b minus a minus 1. And in other words, so we have x to the b minus a minus 1 equal to 0 minus 7. And then x to the b minus a equal to 1 minus 7. So that's what we get here. Okay? So that's how you do things carefully. Okay, if there is no other question, question? Oh, okay. Okay, if there is no other question, then let's go to our more complicated multiplication group. So multiplication group of a composite number p times q. Okay, so let's first see. So we can let the number of integers from 1 to n minus 1, or actually 0 to n minus 1 is also considered. But anyway, from 1 to n minus 1 that are also coprime to n, the number here we say is p minus 1 times q minus 1. And let's build some intuition first. So why is this true? That's because, so first think about how many things. So we want everything to be mod n, right? So only need to count from 0 to n minus 1. So how many of those things are coprime to p times q? Well, if you coprime to p times q, then you need to not have a factor of p and not have a factor of n, q, right? So how many how many elements are here? Obviously you start with n elements, and so if you want to be coprime to p, well then you like do a division by p and count the remainder, and the possibility are like 0, 1, 2 to p minus 1, and if everything is distributed uniformly, then the probability you are coprime to p is p minus 1 over p, right? Because you have p possible result, and one of them is you have a factor of p. Okay. And similarly, then you think about pq. So if you take a totally uniformly random number, what's the probability that is coprime to q? So q is a prime, so that's q minus 1 over q. Because you have 0 to q minus 1, and only if the remainder is 0, you have a factor of q. Yeah. So the number of things coprime to n should be n times p minus 1 over p times q minus 1 over q, and n equal to pq, so that's just equal to that number. Okay, just equal to p minus 1 times q minus 1. Okay, so that's what happens when everything distributed uniformly and nicely. But is that actually true? Well, we cannot is true, and we are going to prove it. But I guess before we prove it, we see it in an example. So the thing is, this counting of the remainder by p and the remainder by q is actually correct. So everything inside this group is actually just labeled by its remainder p and the remainder q. So let's see this with the smallest possible example. Not quite small as possible, but as small as possible without 2. So p equal to 3, q equal to 5, and n equal to 15. Then then p minus 1 equal to 2, and then q minus 1 equal to 4. So we have 8 elements. And we can see we can just characterize the 8 elements by its remainder to 3 and the remainder to 5. So we have this table here. So we want things to be corresponding to 5, so when we divide by 5, the remainder should be either 1, 2, or 3, 4. 1, 2, 3, 4, one of those. And when we divide by 3, then you can have the possibility are 1 or 2. Yeah. And you see that actually you have the A possibility here. So if 1 that has remainder 1 that divided by 5 remain 5, and 1 divided by 3 will give you also 1, then you have a 2. Obviously remember 2 and 2. And 3 is not good, right? Because 3 minus 3 is equal to 0. So it's not co-prime to 15. And we have 4 here. So 4 minus 5 equal to 4, and 4 minus 3 equal to 1. And 5 is not good again because 5 has a factor of 5. And 6 is not good because 6 has a factor of 3. And we have 7. 7 minus 3 equal to 1, minus 5 equal to 2. And 8. 8 and minus 3 equal to 2, minus 5 equals 3. And 9 is not good again because 9 has a factor of 3. And 10 is not good because 10 is a factor of 5. Then we have 11. 11 minus 5 equal to 1, and 11 minus 3 equal to 2. 12 has a factor of 3. And 13 minus 5 equal to 3, 13 minus 3 equal to 1. And then finally 14. So 14 is minus 1. So 14 minus 5 equal to 4, and minus 3 equal to 2. And that's all of them. Okay? So you see that this table is actually perfectly filled out with 8 non-coprime numbers. Okay? And okay, so that's an example, but there is actually even more structure here, and that's called Chinese remainder theorem. So what we do is we just count from 1 to 14 and try to fill all these tables. But what if we just want to look at the 2 coordinates of this table, and we want to find out what's the number that should be inside? And there is actually a way to do this. That's the Chinese remainder theorem. So the trick is you need to look up 2 metric number. Okay? So that is 10 and 6 here. Okay? So what's cool about 10 and 6? Well, they are not inside, but so 10 is multiple of 5, right? 10 is 5 times 2. While it's also but when you multiply 10 with 3, it equals to 1. Okay? And 6 is similar, but you reverse the 5 and the 3. So 6 is multiple is so 6 is a multiple of 3, and but when you take 6 multiply, it equal to 1. So once again, 10 and 6 is not in this group, but it will be very useful to generate this table. That's because now you think about you want to take some coordinate A, B on this table. So let's say the coordinate. So let's say I think this is A and this is B. Let's see if I get this correct. Okay. So if you want to find the AB's coordinate on this table, then you can just calculate 10 times A, so this is 10, and 6 times B. Okay, so what will happen? So you have 10 times A plus 6 times B, and then obviously you should have, so let's put red. So you have to calculate 10 times A plus 6 times B, then obviously you need to mod 15. Okay, because everything mod 15. And why does this just give you the correct coordinate? That's because you think about how this mod 3 and mod 5. So 10 times A plus 6 must be, and you want to so you want to divide this by 3. Then 6 is multiple of 3, right? So when we take mod 3, then this part just disappear. And now I think about 10 times A mod 3. But 10 is equal to 1 when mod 3. So that's just equal to A. Okay? And similarly, when you take mod 5, then this is reverse, right? When you take this in mod 5, then 10 times A, because 10 has a multiple of 5, so this is 0. And you have 6 times B and mod 5, but 6 equal to 1 mod 5. Okay, so my 5 and 3 look similar. 6 equal to 1 mod 5. Okay. Anyway, yeah, so 6 equal to 1 mod 5, so that's just 1 times B, so that's B mod 5. Okay. So you see that if you calculate this in the whole integer, so you calculate this 10 times A plus 6 times B, and mod 15, then this number will be equal to A when you mod 3 and equal to B when you mod 5. Yeah. So that's very cool. And alright, so we have an example here. So we have an example A equal to 2 and B equal to 2. Then 10 times 2 equal to 20, and 6 times 2 equal to 12. Then you get 32, and then you mod 15, you become 2 here. Okay. So that's how you can fill out the table without just enumerating everything. Okay. And so you see that this AP notation for things inside this modern group is actually very useful, because it tells you a lot of structure about this group. Basically, this mod 3 part and this mod 5 part act independently when you do multiplication. So, for example, you think about some number that has coordinate AB inside this table, and you multiply it with another number that has coordinate CD in this table, then that will become a number that's AC on the first coordinate. So basically AC mod 3 and BD mod 5 on that table. So let's see. So when you do multiplication, basically you do a multiplication on x-axis and then multiplication on y-axis. And for example, let's see, how should I pick? So we have to pick A, B equals this, right? So whatever CD, let's say, is this. Let's see, does this work out? So we have AB. So we have AB equal to 2, 2, and then times CD equal to 1, 4. Okay? 1, 4. And that should be equal to the quadrant mark. So we predict it is equal to 1 times 2 equal to 2, and 2 times 4 equal to 8, but 8 minus 5 equal to 3. Okay. So is that correct? So this is actually 2 times 4 equal to 8. And we see that's correct. 2 times 4 equal to 8 is here. Okay. Magical. It works out. So it's 2, 3. Okay. Okay. So that's pretty cool. And okay. I guess we keep going. So that's some digression, but let's go back. So let's go back to actually prove this claim. Okay. And so why is this true? We kind of see it, but let's putting it more rigorous. So we start with okay. Anyway, so phi n equal to p minus 1 times q minus 1, and so we split it into two parts. So hard part and easy part. Hard part is prove that psi n is bigger than p minus 1 times q minus 1. And the easy part is to prove that p minus 1 times q minus 1 is greater or equal to psi n. If both of these, then obviously psi n will equal to p minus 1 times q minus 1. So first part we kind of already do. So the first part is do by saying that wherever you have PQ, then you can write all this table, and you can always fill this table with numbers. Okay? And yeah. Okay. Yeah. Yeah. So you can always fill this table with numbers. So whatever slot there is, there must be something inside this group that that when you mod p equal to the coordinate a, when you mod q equal to coordinate b, and it's coprime to pq. Well, obviously, other than that's coprime to pq. Yeah. But there's always something, so every AB must have something, and we prove this by constructive proof, just by doing this Chinese remainder theorem. Okay, so we say that for every A, that's a coordinate in this, or it's actually y-axis. So A in this y-axis and B in this x-axis. So A from 1 to q minus 1. So this notation means 1 to q minus 1. And sorry, that's P. So 1, 2 to P minus 1. To P minus 1, and it is 1, 2 to Q minus 1. So anyway, so we have an A coordinate and a B coordinate. Then you can always find some number inside, because the Chinese remainder theorem magical number is 10 and 6. Now we have a magical number A and B, they always exist. So they are basically the 1, 0 and the 0, 1, although the table don't list 0 here. But we think about mod P and mod Q, they are 1, 0 and 0, 1. They always exist. So the Chinese remainder theorem says that you have, I should have said a little more here, right? So A such that, so A is, so A equal to 1 mod P, and Q divides A, and B equal to 1 mod Q, and P divides B. Okay. So A, B satisfy this, and so now when you try to fill the table, so you want to find some coordinate A, B, then you just have big A times A and big B times small b. Then when you try to divide by P, you see that so B is a multiple of P, so this doesn't matter. And A mod P equal to 1, so this is also just equal to small a. Then Q is just things reverse. So Q is just things reverse, so is A is a multiple of Q, and B is equal to 1 mod Q, so this is equal to small b. Okay. And so you see that you can just take big A times small a plus big B times small b, then mod PQ, and you can then you find you can fill in the slot inside this this table. So you see that every slot of the table can be filled in. Right? So for every AB in this Q minus 1, P minus 1, and Q minus 1, there exists some number inside the group. Okay. And obviously, when you have some pair A prime, let's just say okay, so also obviously if you have A prime B, AB, so if you have another number, so also need to prove that every slot in this table are different, right? But that's very obvious. So if you have A prime, B prime, not totally equal to AB, then obviously FAB not equal to FA prime B prime. Because, well, if they are equal, then then they should be equal mod P and they should be equal mod Q. But they are not totally equal when they mod P and mod Q, so they are different. Okay? So anyway, let's go back. So we proved that psi n is at least P minus 1 times Q minus 1, because we can construct this P minus 1 times Q minus 1 table, and we found out every slot you can find the corresponding element in psi n. So psi n need to have at least P minus 1 times Q minus 1 elements. Okay? And also all the elements are different by this short proof. Okay? Anyone has question? And also I guess we can do a very short proof of the Chinese remainder theorem. It's just because let's say it's big A, right? So big A you can just found that big A just equal to Q times. So we actually already proved this, because big A is multiple of Q. I guess it's a little different, but okay, we just need the existence, so let's do this in a stupid way. So we just think about Q Q to the R. So we think about Q inside the multiplicative group of P, right? So there exists some order Q to the R equal to 1 mod P. Right? So then we can just define Q to the R equal to A. Okay? Hopefully that's okay. So but that's aside. So If you can get this, you can get this, but don't get too confused. So let's go back. Let's go back to our current label. So anyway, we proved that this q minus 1 times p minus 1 times q minus 1 table can be filled out, and every slot different element. So you must have at least p minus 1 times q minus 1 element. Then then we go back to the easy part. So p minus 1 times q minus 1 must be bigger than the number of elements inside your component group. So basically there are no other elements. And this is kind of a dumb proof. But anyway, so let's suppose that we have two numbers f and g, okay, such that we have two numbers f and g such that so they occupy the same slot inside this table. So basically we want to prove this table is unique, because obviously everything can be put inside this table, right? Because you can take a remainder of p and take a remainder of q, and they must give some number. So what we are trying to say is, so we prove that every slot must have one number, and every slot are different. But now we want to prove that every slot can only have one number, so uniqueness of every slot. So let's say if some slots have two different numbers, f and g, okay? And then without losing generality, we assume f is bigger than g. We also say equal, so it's a little easier. Okay. So f is bigger than g, and they are coprime to n, so and we have everything mod n, so it's from 1 to n minus 1. And as we say, f and g occupy the same slot. So f equal to p mod p, and f equal to g mod p, and f equal to q mod q. What am I saying? So f equal to g mod p, and f equal to g mod q. Then we think about f minus g. Okay. So things actually happen here, this step. So we think about f minus g. So f minus g must be, well, mod p equal to 0 and mod q equal to 0. And then once again, with our fundamental theorem of calculus, it means that it must pq equal to 0. Okay, this is where things happen. And okay, so f minus g mod pq equal to 0. And but then we already say f minus, so from our characterization here, so f minus g is something from 0 to n minus 1. And the mod pq, the mod n equal to 0, then it's a multiple of n, but it's in this range, so only possibility is f minus g equal to 0. Okay? So let's say f minus g equal to 0, and I should have, so let's write down this a little slower. So f minus g mod n equal to 0, so that means f minus g f minus g, wait, why am I writing g as q? F minus g equal to some number times n, and together with this, those two together, we have, but is that 10 equal to some number times n, but it's from 0 to n minus 1, so it means s minus g equal to exactly 0, so f equal to g. And yeah, so we prove that every slot is unique. Okay? Question? Okay. So this is a little digression. Actually, we don't need this in ISA, but it's nice to learn this structure of this multiplication group of n equal to pq. Okay. If not, and now we have about 20 minutes. We can maybe finish our essay. Let's see what happens. Anyway, let's keep going. So now we have more group theory, and group theory that we don't quite need. But every finite abelian group actually have a very nice structure result. It says that every finite abelian group you can just decompose them into a whole bunch of cyclic groups. And I guess, okay, it's a little different. It's a different thing. We don't quite need to use, so let's skip this. And anyway, we know that if you keep multiplying things, then I think this is the important part. Anyway, so if you keep multiplying things, then you will get a subgroup. And as we say in last class, the order of a subgroup will divide the order of your whole group. Okay. And now the RSA thing is that, so if you are given PQ, then you can obviously calculate psi of n. Okay? And so the PQ and the psi are basically a secret key in your encryption. And but the public key will be your n. So the thing is, if you are given n, then it seems pretty hard to get a PQ because of factoring. And also, it also seems hard to get psi of n. Okay? But it might be easier, but it also thinks we don't know how to get this. But anyway, the RSA way to break the shortest way to break RSA is given n, then you can factor PQ, then you can get psi of n. So that's the secret key. But if you are not given PQ, then some calculation around psi of n seems to be hard to get. Okay. So finally, let's go to RSA. Okay. So, well, it's a public key encryption system. So let's see how it works. So first we start with construction phase. So as we said, we want two prime numbers that are hard to guess. So we have two random large prime numbers, P and Q. And as we said, we want n and phi. Okay, so the encryptor will calculate this n equal to p times q, and we will calculate this phi n equal to p minus 1 times q minus 1. And we need to pick a random encryption key, so it's just a random number, but it needs to be something inside the multiplication group of n. Okay, so we want okay, sorry, it's different. Sorry. It's in the multiplication group of psi n, I think. So anyway, sorry, it's a little confusing. Anyway, you have an encryption key E, and it just need to be copied to this psi n. Okay. Then okay, let's see. Okay. Anyway, so we have an encryption key E is going to be public, and then now there is a secret here. So I think this is public, and this is a secret, and E is also public, and then you have a secret decryption key. So secret decryption key is going to be something equal to 1 modifier. Sorry, so it's something that when you multiply E with D, so it's the inverse of E inside the multiplication group of phi n. Okay. So this is a little confusing because we keep talking about multiplication group of n, but now we are doing multiplication group of phi n. Okay. But anyway, that's what we do. And this can be done actually efficiently. So this is inversing. So if we say order finding, you cannot do efficiently, but actually, order finding you cannot do efficiently, but inverse you can do efficiently. And we'll see this with an example later. But basically, you need to do the extended Euler's algorithm. And extended Euclid's algorithm. So what you do is you run the algorithm that find the GCD of E and phi n, and you reverse the calculation, then you will find this D. We'll see probably next time because we are much slower than I expected. But anyway, so this is how you calculate all the things you need. And now finally we see the operation. So this encryption system is a public key encryption system. So it works like this. So you have a server and there's a user. And the server will send out public keys to a user, and the user can send out encrypted message. And the server also holds some secret here. And the point is that only server can efficiently decrypt the encrypted message with its secret here. Okay. And so some bad guy outside. So bad guy also get a public key, but bad guy can see the public key, can see the encrypted message, but bad guy cannot really decrypt it. Okay. So as we said, so server will send the big number n, so n equal to PQ outside, and why do I? Okay, yeah. N equal to PQ outside, and also encryption E, which is just a random number corresponding to phi, as a public key out. Okay, so now what does user want to do? User want to encrypt some message M. Okay, and let's assume n is not enough, so n is just some number that's corresponding to n. Okay, let's assume we are lucky. Okay. Although it has some chance, but let's say PQ is very large, so n has a high probability to be corresponding to n. Okay. Yeah. And then the user will encode its message by just doing this. So you will calculate n to the e's power, and mod is begun. Okay, now we are back to the multiplication group of begun. Okay. And that's the message. And the server will decrypt by calculating n prime to a d. And so everything is in mod n. So n prime to a d, which is equal to n to the e to the d equal to n to the ed, and that actually equal to that equal to 1. This is actually equal to 1. How should I say? Yeah. Anyway, and I should just say this n to the ed will actually equal to n mod n. And we'll have the proof here. Okay. And this is the only part we actually need to use all the group theory we talk about. So why does n to the ed equal to n mod n? Okay. That's because, let's see if I can C. Okay. Okay. So remember by definition we have that recall that we have ED equal to 1 mod phi, right? Mod phi n. Okay. And so ED, so D is E's inverse under mod phi n. I should have not have. Okay. Okay. So ED equal to 1 mod phi n. So now we think about ED minus 1. So n to the ED minus 1. Well, so ED minus 1 must be some multiple of phi n. Right? Okay. So this is just this thing. And and then we use our group theory here. Okay. So we think about a little confusing. Oh, okay. Okay, so this is a little confusing. So yeah. So we have phi n up here. Then now we remember this R thing. So we think about remember we have, if I have is m and m squared, m cubed, all the way to m to the r minus 1. This is a subgroup in this mod n, right? In this multiplication group of n. Okay? This is a subgroup in this mod n group. In this multiplication mod n group, right? And once again, we know there are R elements. Okay? Okay. And okay, so this is where all our discussion on the multiplication group mod n is useful. And we know phi n is the order of the whole mod n group. And now this exponentiated, so this subgroup generated by m, this exponentiating subgroup is a subgroup, and it has R element. And by our group theory result, we know the order of a subgroup must divide the order of the whole group. Okay? So R must divide phi n. Okay? So that's the important part here. Okay? And then once we have this, we are basically done. Okay? So you see that phi n, so R will divide phi n, then phi n equal to some number, we just call it C prime times R. Okay? Then this whole thing is just R times whatever number C times C prime, we don't really care, because that means it's n to the R 2 times some C times C prime. And well, n to the R equal to 1 mod n. So 1 to whatever power is still 1, so this is 1 mod n. Okay. So yeah, that's basically it. So we prove RSA work because we have n to the ed minus 1 equal to 1 mod n. Then you multiply both sides by m, then n to the ed equal to m mod n. So we prove how the RSA description work. You have this weird d that's the inverse of your random equation E, key E, under mod phi n. Then you see your encrypted message n prime, then you just multiply it with d. You just exponentiate it d times. then you will get back your original message mod n. Okay. So that's the RSA system. And the thing we need to use is this subgroup of n to the r's power, and we know that r is a factor of this phi n. So then you know this phi n is just a multiple of r. Okay, so this is the weird step. Okay. And over 2 minutes, maybe you can do this extended Euclid. Okay. And okay, so now let's see how we do inverse of a multiplication group very fast. Okay. Let's say P. Okay. I guess this is the whole thing. Another Euclid I forgot to change. Euclid. Whole thing. Actually, sorry. This is the whole RSA goes through. So we have our favorite PQ equal to 3 and 5. And the order of the multiplication group is 8. Because 2 times 4 equals 8. And we pick a number that's coprime to 8, and let's say it's 3. And first let's see how we calculate the d here. So that's the Euclid. So first we see the GCD between 8 and 3. And the Euclid algorithm runs this, so you just divide each other back and forth. So you divide 8 with 3, so you will get a minus 3 times 2 equal to 2. Then you want to divide between 3 and 2, so you have 3 minus 2 equal to 1. And then you can reverse this 1. So then you reverse this 1 equal to into a linear combination of a and 3. So you see 1 equal to 3 minus 2. And then you write this 2 equal to a minus 3 minus 2. So now everything is in factor of 3 and 8. Then you write 3 times 3 minus a equal to 1. And okay. Then you take mod a on both sides. Then you see mod a on this side, obviously 1 mod a is still 1. And when you mod 8, then this 8 disappear. So you have 3 times 3 equal to 1 mod 8. And you know the d is also equal to 3. Okay. So that's how you find d. So happen to be d equal to e. And yeah, then you can check that it also works out. So you can check n to whatever n to the d will equal to n mod 15. Okay. So here are some examples you can work out. You see it works. So basically n to the 9 will equal to n because n to the 8 will always equal to 1 for whatever n. And you can check this with n equals 7. And sorry for the overtime. So this is a wrap up of Grover's algorithm, the Shor's algorithm for factoring, and the related number theory and RSA. And next time we'll switch gear and talk about Grover's algorithm. Okay. Okay. So see you next time. Why do I have red light? Oh, okay.